Welcome to my video lecture based on utilization of electric power. Paper code TE702. Today's lecture is based on induction and dielectric heating, and this is included in the module of electric heating part. In the last lecture, I have discussed about arc furnaces, then electric induction and dielectric heating introduction part I have covered. Now we will tell much more advanced part of induction and dielectric heating. So in this module, we will mainly concentrate on induction and dielectric heating advanced portions, and also we will solve some numerical problems related to this. Myself, Bhuvan Banerjee, Assistant Professor of Electrical Engineering Department, Dr. Sudhir Institute of Technology and Sports Complex. This institute is formerly known as Dr. Sudhir Degree Engineering College, and it is under GIS group. So let us continue with our topic. So, in case of induction and dielectric heating, there is an effect of frequency. Whatever amount of frequency we choose, based on that, our induction or dielectric heating part will be definitely affected. That part we will discuss now. Selection of frequency or choice of frequency. The selection of frequency for a heating is important because it has great bearing on the work to be heated and the method of heating, either by induction or dielectric heating. Furnaces running on the power frequency of 50 Hz can be of 1 megawatt capacity, whereas those running on medium frequencies like 50 Hz to 1000 Hz have a capacity of 50 kilowatts. And those running with high frequency, that is 1 to 2 megahertz, have capacities ranging between 200 to 500 kilowatts. That means with changing frequency or with increasing the amount of frequencies from 50 Hz to 500 Hz or 1 to 2 megahertz, the amount of range of heat amount will be also changed. So let us see what are the effects of induction heating in case of frequency. While choosing frequency for induction heating, the following factors are considered. Factor 1, that is thickness of surface to be heated. Higher frequency, thinner the surface will get heated. That means with higher frequency and thinner surface, that will get heated. So definitely there is the effect of thickness of the surface which is to be heated. Definitely that will affect by frequency, amount of frequency. Now, next part to be considered, that is the time of continuous heating. Longer the duration of heating, deeper the penetration of heat in the work due to conduction. Option C, the temperature to be obtained. Higher the temperature, higher the capacity of the generator heat plant. So there are three main things we can discuss. Point 1, that is thickness of the surface to be heated. Higher the frequency, thinner the surface that will be heated. And second condition is the time of continuous heating. Longer duration of heating, deeper penetration of heat in the work due to conduction. And third part is the temperature to be obtained. Higher the temperature, higher the capacity of the generator is required. Next part we will discuss about, that is on dielectric heating. consumed by the dielectric is, that is C equals to 2 pi F C V square. And tan delta, that means P equals to 2 pi F C V square tan delta. As seen, P is directly proportional with F square. Hence, rate of heat production can be increased by increasing voltage, or voltage across specimen is limited. By its thickness, or because of the consideration of potential gradient, breakdown voltage and safety etc., voltage ranging from 600 to 3000 volts are used for dielectric heating. All the voltages of 20 kV or so are also used sometimes. Rate of heat production can also be increased by applying high potential, but it is also limited because of the following considerations. A. Possibility of formation of standing waves between the surface of two electrodes having wavelength nearly equal to or more than 1/4 of the wavelength of particular frequency used. Then B. Necessity of employing special matching circuit at higher frequencies due to the fact that maximum power transfer takes place when the oscillator impedance equal to the load impedance. C. At higher frequencies, it is difficult for tuning inductance to resonate with charge capacitance. And D. The higher frequencies, it is almost impossible to get uniform voltage distribution. E. Since higher frequency disturb nearly radio station services, special arrangement has to be made to stop radiations from higher frequency generator used for the purpose. So these are the points we have to consider about dielectric heating. Now let us take some examples related to heating, electrical heating. So example 1. A resistance oven employing nickel wire is to be operated from 200 volt single phase supply and is to be rated at 16 kilowatts. The temperature of the element is to be limited to 1170 degrees centigrade and average temperature of the charge is 500 degrees centigrade. Find the diameter and the length of the element wire. Radiating efficiency is 0.57, emissivity 0.9, specific resistance of the nickel is given at 109 into 10 to the minus 8 ohm meter. Solution. The values that is given, that is voltage, that is 220 volts, power 16 kilowatt, temperature 273 plus 1170 to make the centigrade to Kelvin. And temperature, another temperature that is given 500 degrees centigrade, that is converted to Kelvin by adding 273. Now efficiency, radiating efficiency 0.57, emissivity 0.9, specific resistance rho of nickel is 109 into 10 to the 8 ohm. Now we know that L by d square equals to pi d square divided by 4 rho P. So putting all those values, we are getting that L by D square equals to 2179660. Now again, H equals to 5.57 epsilon radian E into T1 by 100 whole to the power 4 minus T2 by 100 whole to the power 4 W by meter square. So we are getting that H equals to 115729 watt per meter square. So that is the amount of heat. So we know that L by D square equals to 2179660 and H we are getting that 115729 per meter square. That too we have calculated. Now the total heat dissipated per second equals to the electrical power input. So the factor will be pi into 1 into 115729 equals to 1600, the electrical power input. And we know that PL equals to 0.044. So calculating, we are getting that D square L square equals to 0.001936. So multiplying these two equations, we have got L equals to 16.16 meter and D equals to 2.27623 milliliter. This part we have calculated from this. So this is the problem related to resistance of an employing microwatt. Now we are going to another problem. The following data related to a 3-phase arc furnace. Quantity of tin to be melted in 1 hour is 4.3 pounds. Specific heat of tin equals to 0.5 kilojoule per kg degree centigrade. Latent heat of tin is 37.2 kilojoule per kg. Melting point of tin equals to 1370 degrees centigrade. Initial temperature of this tin is 19.1 degrees centigrade. Overall efficiency of tin is 2%. Input current 5700 ampere. Resistance of transformer effect secondary 0.008 ohm. Reactance of transformer effect secondary is 0.012 ohm. Determining the following. Question 1. Average kilowatt input to the furnace. Question 2. What is arc voltage? Question 3. Arc resistance. Question 4. Power factor of the current drawn from the supply. And 5th question. Average kVA input to the furnace. So that is the figure it is being given. So let us go to the solution part. So M was given 4.3 pounds, that is 4,300 kg time 1 hour. C equals to 0.5 kilojoule per kg degree centigrade. N equals to 37.2 kilojoule per kg. Melting point T3 equals to 1370 degrees centigrade. Initial temperature of tin equals T1 equals 90.1 degrees centigrade. Epsilon beta equals to 50 degrees per 50%. I equals to 5700 ampere. R equals to 0.008 ohm. X equals to 0.012 ohm. Now average kilowatt input to the furnace, that is energy required to melt 4.3 tons of steel. So you need to see into T1 minus T2 plus ml equals to M into C, that is T1 minus T2 plus L. So 4,300 and all the values I have put here and got the value average kilowatt input to the furnace, that is 851.2 kilowatt hour. Now we will calculate the average output by total energy required in kilowatt hour divided by the time of melting in hours. So we are getting that 851.2 kilowatt. Now for average input, we will do average output divided by the overall efficiency, that is 851.2 divided by 0.5, that is 1,702.4 kilowatt. So that is the average input we are getting. Now arc voltage Q equals to voltage drop due to transformer resistance, that is 5,700 into 0.008, that is 45.64. Next, voltage drop due to transformer reactance, that is 5,700 into 0.014, that is 79.84. Now open circuit secondary voltage from the figure we can calculate that. Interval VA plus 45.6. This is the figure. This is VA plus 45.6 plus 79.8 square. So we are getting that. This is the open circuit secondary voltage. Now for calculating the power factor, it will be VA plus 45.6 divided by VA plus 45.6 whole square plus 79.8. Total power input equals to 3 into power drawn from power phase equals to 3 into current drawn per phase into secondary voltage into power factor. So putting all these values, we are getting then the value of PA at arc voltage, that is 64 volts. We have calculated that arc voltage value is 64 volts. Thirdly, arc resistance RA equals to PA by I, which is 54 by 5,700. We are getting that 0.00947 ohm. Fourthly, power factor cos phi, we have calculated. We are getting that the power factor value is 0.7804. Next, average KVA in the furnace, which will be KVA in the furnace, that is equals kilowatt input divided by the power factor. So the value is 2181.4 kVA. So these are the four values we have calculated from this topic. Now, next problem. Calculate the efficiency of a high frequency induction furnace which takes 10 minutes to melt 1.8 kg of aluminium. The input to the furnace being 4.8 kilowatt and initial temperature 15 degrees centigrade. Specific heat of aluminium, that is equal to 0.88 kilojoule per kg degree centigrade. Melting point of aluminium, that is 660 degrees centigrade. Latent heat of fusion of aluminium is 32 kilojoule per kg, and 1 kilojoule equals to 2.78 into 10 to the power minus 4 kilowatt hour. The solution is we are getting that U M equals to 1.8 kg. Input to the furnace is 4.8 kilowatt. T1 equals to 15 degrees centigrade, T2 equals to 660 degrees centigrade, C equals to 0.80 kilojoule per kg, L equals to 32 kg per kilojoule per kg, and 1 kilojoule equals to 2.78 into 10 to the minus 4 kilowatt hour. The efficiency of the furnace equals to heat required to melt 1.8 kg of aluminium, that is M into C into H minus T1 plus M into M. That is the formula we have used here, and this is the formula we have used for cooking problem. This is the formula we are used, and putting these values we are getting that the energy input is 0.8 kWh. The efficiency we have calculated by output the input, that is 37.5% we are getting. And this is the small problem, and this is the solution of that. So I am finishing this lecture here. In my next lecture, we will again discuss about utilization of electric power, heating, electric heating part, and various numerical problems I have discussed here. In my next lecture, we can also discuss some theory and some numericals related to electric heating also. So I have taken this course from the book of Sadhu and Das of utilization of electric power. You can go through that book. It's very important and efficient for your understanding purpose. And I will refer this book. You can also go to the book of utilization of electric power. That is also another good book for this figure. So I have finished my lecture today. Thank you all for listening to my lecture.